maybe. Come on, there we go. All right, so today we're continuing with 2.6, which was polynomial inequalities. So when we did them on Friday, we just talked about the quadratic inequalities. Now we're going to talk a bit higher order polynomials, higher degree inequalities here. So we're talking mostly cubics, but higher than that could show up. It's mostly going to be cubics though. And so we're going to talk about strategies for solving those. So grab whatever you're using to take notes and let's get going. P-H-E-R, degree, polynomial inequalities. Higher degree polynomial inequalities, and just like Friday, we want to be able to solve these and show our answer using a graph, a number line graph, or also using set notation. So here we go. These are going to work much the same way that they did on Friday. So our first example, we're going to have x to the third minus 3x minus 2 is less than 0. Okay. Now this is not something that I can factor super nicely. So what I would do instead, there's actually a couple avenues you can go with this. The first way is to use, or the way that the book suggests anyway, is to use what we learned back in the previous couple of sections with trying to guess possible zeros and then use those to divide them out to test if it is a 0, and then being able to factor what's left over and all that sort of thing. You can definitely do that, and I'll show you how to do it. But graphing is probably going to be our most efficient way to find our actual zeros here. So if you want to, you can remember that, okay, the last term, if I were to write down the factors of that, we have plus or minus 1 and plus or minus 2. And then the leading coefficient was 1, so we divide it by the factors of the leading coefficient. And this would tell us positive 1, negative 1, positive 2, and negative 2. Those are all of our possible roots, or our possible rational roots. So then we could use our possible rational roots and go through and check each of these to see if any of them are roots for this, or are actual roots or zeros for this function. But as you might imagine, the more possible rational roots you have, so the more complicated that number is, the more factors it has, the more possible rational roots you end up with. So you could end up testing possible rational roots all day long and spending forever on a single problem. And I'm not a huge fan of that, especially when we have things like graphing. So what I would personally do is take this and graph it. So we get x to the third minus 3x minus 2, and we can see exactly where the zeros are. At negative 1 and at 2. Okay. So, but if you wanted to go through and test, especially since this one is one that doesn't have that many possible rational roots, if you were going to go through and test, I would divide x plus 1 out. To test -1 as being a root, or being a root. So to do that division, I would stick -1 in the box, and then my coefficients are 1, 0, -3, and -2. We'd bring down the 1, we'd multiply, add, multiply, add, multiply, add, and what do you know? It's a root because this number is a 0. We don't have a remainder. So -1 is a 0. And then we're left with x squared minus x minus 2, which is something that we can factor into x minus 2 times x plus 1, which would tell me that my other roots, or all my roots are -1, which has a multiplicity of 2 because it shows up twice, or +2. Okay, but I could easily just find this information by looking at the graph. So whichever way you want to come by your information is fine. Hinder, come on, bud. Must have heard something. All right. So once we find our roots, this becomes exactly like the kinds of problems that we did on Friday. So the only part about higher degree polynomials that's a little bit different than what we did on Friday is the process of finding the roots can be a little bit more complicated if you're doing it by hand. Because they aren't always nicely factorable. So anyway, once we've got our zeros, we do the same exact thing. We make the sign chart. We add our zeros at -1 and +2. So I'm going to plug in x equals 0 here, x equals 5 here, and x equals -2 here. Since those are values that are within those ranges, less than -1, between -1 and +2, and greater than +2. So if I plug in -2, f of -2 in my original equation here, we get -8 plus 6 minus 2, which gives us -4. Plugging in 0, we get f of 0 is -2. Plugging in 5, we get f of 5. 5 cubed is 125. Minus 15 minus 2 gives us 108. So we have a negative, and a positive. So this thing only changes sign once, and we're looking for the cases where it is less than 0. That means we want the negative interval. All right. And something to note here with this one in particular, we want the negative interval, but it has to be strictly less than 0. At -1, f of -1 is equal to 0. F of 2 is equal to 0. So although these are both negative intervals, I need to exclude -1 and I need to exclude 2 from my intervals. So we have it's negative from -infinity up to -1. Then I want to exclude -1 and get the interval from -1 to 2. If it was or equal to, I could just have one big interval from -1 to from -infinity to up to -2. But since it's not, it doesn't have an or equal to symbol, then we need to split it up and not include -1 since the function is equal to 0 at -1. And we can also see this in our graph. We can see here that at -1 it's equal to 0, and since we're looking for the places where this function is less than 0, that means we need to exclude 2. And all of this is negative, except for here. And all of this is negative. So from -infinity up to 2, excluding -1, the whole function is negative. If I were to put in less than 0, we would see that it's happening, but it won't always show you this discontinuity of where at -1 that's not the case. Okay. So this would be our interval. So just be careful with the or equal to when it's not an or equal to symbol. And then we would also have on our graph 2, -1. We'd have open dot, open dot. These would be connected, and then it would continue on forever in the negative direction. Okay. So those are our, that's one possible example of a cubic that we would see as a nonlinear inequality. Any questions from that one? Any numbers we're not sure where they came from? Any steps we're not sure how they happened? Okay. Well, then let's do another one. This one, I'm not going to show all of the dividing out to test roots because that would take a long time. So instead, and it's also fairly pointless because we do have graphing capabilities the majority of the time. So second example, we are doing 3x to the third minus 4x squared minus 13x minus 4 is less than or equal to 2. Okay, so just like with Friday, our first step is to get a 0 over here. So minus 2 on both sides, we get 3x to the third minus 4x squared minus 13x minus 6 is less than or equal to 0. This time we have a less than or equal to thing, so we don't have to worry as much about all the different possibilities of excluding a value in our interval. Okay, so here we go. Personally, what I would do here is go and graph this. You could, again, like we had up here, figure out what to divide out because we'd have the factors of -6. So we'd have negative plus or minus 1, plus or minus 6, plus or minus 2, plus or minus 3. And then the factors of 3, which are plus or minus 1 and plus or minus 3. But then as you can see, we would have a lot more things we need to check. We would have to check plus or minus 1, 2, 3, and 6. And then we also have to check plus or minus 2/3 and stuff like that. So we get up there in the things that we might have to check until we find a 0. So that's why it's probably easier to just graph it. to find the zeros. So we would have 3x to the third minus 4x squared minus 13x minus 6. And we can see we do get some zeros here. We get -1, -0.667, and +3. If you were asked for exact values here, you could either recognize that -0.667 is -2/3, or you could take one of your zeros like -1 and divide that out and then factor what you have left. Either way. So we end up with our zeros being -1, -2/3, and +3. And you can even continue here from the graph if you want to. We're looking for places where it's less than or equal to 0. So we're going to have this interval here up until -1, where the function is less than or equal to 0. And then we'll have this interval in here from -0.667 to 3, where it's also less than or equal to 0. You can always do it the sign chart way as well. Again, this is kind of a way that assumes that you don't have graphing capabilities. No, we do. You could make your sign chart, and we'd have -1, -2/3, and +3 on it. And the sign chart's even helpful if you don't choose to plug in values and everything. You can still look at the graph and kind of note on your sign chart where the function is positive and where the function is negative. It's a helpful thing to help kind of keep track here. But for this one, I might check x equals 4. In here, I might check x equals 0. Here, I might check, that's going to be a little bit tougher, x equals -5, 6, since that is between these two. And here I might check x equals -2 or something like that. Okay. The nice thing is if you type f of x equals before this and you want to plug in a value, you can just type things like f of -2. And know that f of -2 is -20. Or f of -5, 6, which is positive 0.319. Or f of 0 and get -6. Or f of 4 and get 70. So however you want to do it, you can, or you can just notice in here that, again, it's positive in this interval, it's negative in this interval, it's positive again, that sort of thing. Either way, we note that this is negative, then it goes positive, then it goes negative, and then it goes positive again. And since we're looking for less than or equal to 0 intervals, that means we want negative infinity to -1 inclusive, since it's or equal to. And then we want this interval as well, the -2/3 to 3, inclusive on both ends, since we have that less than or equal to. So this would be one way of expressing our solution. And the other way to express it is with the number line. So we'd have -1, -2/3, and 3. And we have a solid dot on the -1 and an arrow pointing off to the left. And then we'd have a solid dot on each of these and a line connecting them. Okay. Any questions with that one? Any numbers we're not sure where they came from? Any steps we're not sure how they happened? Okay. If you do have any, unmute yourself and say so, or type in the chat. But I'm going to give you guys one to try, and then we will kind of move on from there. All right. So the one for you to try is going to be nice. We'll go with 2x to the third minus 9x squared minus 20x plus 12 is less than or equal to 0. All right. There's one for you guys to try. When you think you have it, type done in the chat. Keep in mind, a good first step might be to graph the thing. If you got -2, 1/2, and 6 for your zeros, you're on the right track. If you're looking to check your work, those would be the zeros that we find either by graphing or by guessing and dividing. You can even fill in the sign chart just by looking at the graph if you would like. Notice that it's negative up until -2. Then it becomes positive in the interval from -2 to 1/2. Then it becomes negative again from 1/2 to 6. And then it becomes positive again after 6. So you could fill in your sign chart in that fashion if you would like. Or you can go, okay, well, x equals -3 would be there. X equals 0 would be in that interval. X equals 1 would be in this interval. X equals 10 would be in that interval. And then figure out f of each of those things. Since we want the negative intervals and it's less than or equal to, we would pick -infinity to -2, inclusive, union with 1/2 to 6, inclusive. And then on the number line, close dots on the 1/2 and on the 6, close dot on the -2, and an arrow going left. Okay, so those are our solutions. So this is going to look a lot like what we did on Friday, just less actual factoring involved, because a lot of these things don't factor nicely. Any questions at all? Anything about this particular one or about any others that we've talked about so far? Okay. There's nothing there, then go ahead and over on the poll. Under polls, there's a question. Ready for the homework, or we want more examples? Go ahead and vote. What are we feeling like? Okay. Looks like a majority says homework. So for those of you who would like the homework now, I will post it and talk about it briefly. For those of you who would like more examples, feel free to stick around afterwards and we can go over as many examples as you'd like. Okay, so looking at Google Classroom, our homework today is in IXL. It's going to look a lot like our homework from Friday. We have 2 sections. It's the same kind of sections. We're going to have graph solutions to higher order or higher degree inequalities. And then solving them, writing our answers in interval notation. And on a lot of these ones, it's already nicely factored for you. Like here, it factors it at x minus 4 cubed. That tells you that the only 0 for this thing, the only real 0 here, is -4 or +4. You can still graph it and take a look at what it would look like if you'd like. So we get x minus 4 cubed. And we see our 0 over here. And again, so 4 is going to be our only 0 for this one. and it's greater than or equal to 0. So we want the closed dot. And then we want places where it's greater than or equal to 0. So looking at our graph, it's when x is greater than 4, then the function is greater than 0. That's when the function is positive. So that would be our solution. Okay. Keep in mind close open dots depending on whether it's less than or greater than or equal to and whatnot. And then over here, it's the same idea. Just expressing it in terms of interval notation instead of a graph. Okay. So those of you who are ready to work on the assignment, you are free to go and work on it. Those of you who would like more examples, stick around and we will do more examples.